Hello everyone, welcome to my lecture number 5 for the first week. In this lecture, I will cover problems and solution based on the all 4 lectures we have already delivered. So, there will be some problems which is very tedious to do it, and that's why we have technically chosen those problems to give you the real feel of the real sequences. So, solution of those problems using concepts of limits of sequences are also included in this lecture. Problems and solutions. So, the first question, as you can see here on the board, if limit an be a sequence and limit n tends to infinity an is equal to a, where a is not equal to 0 and an is not equal to 0. That means a sequence an is given which are non-zero, each term are non-zero, and the limit point is also non-zero. Then so that the limit of 1 by an is equal to 1 by a. That's very good questions, and you use the definition of limit of sequences to prove that one. So how do we have to prove? For proving this problem, you have to just take epsilon in such a way that it will comes out as per demands. So as you can see here, since limit of a sequence is given a, therefore I am going to use the definition of limit of sequences. And what was the definition of limit of sequences? For any given epsilon greater than 0, there exists a natural number m1 such that an minus a modulus is less than, I have just adjusted this epsilon is less than epsilon, but I have chosen epsilon in such a way that will fulfill my criteria. So 2 epsilon modulus a square for every n is greater than or equal to m1, and for 1 by an minus 1 by a, since it can be written as taking LCM of the denominator terms, a minus an divided by modulus a into modulus an. Each modulus of an is nothing but a real number. So I can choose in such a way that it will be in denominator, it will comes out half or twice of modulus of a square. So this will be the same as that one, and henceforth if I choose m equal to maximum m1 and m2, then 1 beta n minus 1 beta n is nothing but it is less than epsilon. And by the definition of a sequence, this sequence is going to converge at 1 beta a. 1 beta a here as a limit point L, and 1 beta n is the sequence terms. So this is the nth term of the sequence, and that's the proof of this problem. Second problem, look at this problem. So if limit an is equal to a, so that any constant k into an is equal to k. I mean, look at here, an is this one, kn is here, and k is equal to here. So k can be taken as any constant, and we have to prove that if I multiply each term of the sequence by some constant k, then the limit point of that sequence is also multiplied by the k times. That is our problem. So we will use the algebra of the limits. So we have seen in algebra of limits that limit u into v is nothing, or limit an into bn, So let me erase first. So what we have already learned in algebra of limits, limit an into bn, product of the two, this is equal to individual one, limit an into limit bn, and this will be, if limit an is a and this will be it is b, then ab. So I am going to use this one, right? So k into an, so limit k into limit an. Limit k is a constant sequence. K is just a constant number, so that's why it's a constant sequence. We can treat it as a constant sequence. Henceforth, its limit is k, and limit an is given a. So the answer is k into a. Third one, based on the above one, can you show that limit 1 beta n square tends to 0? That's the question. So we already know that 1 beta n, a sequence 1 beta n converges to 0. So it has a limit point as 0. Therefore 1 beta n square can be written as with the help of limit a and b and product algebra of the product of the limits. So limit 1 by n square can be written as limit n tends to infinity 1 by n, 1 by n. So this will be, that means in the individual product. So limit 1 by n, limit 1 by n. Since these are in a limiting case, that's why its answer is 0. You cannot multiply 0 by 0. But here, as you can see here, these are in the limiting case. It's very near to 0. It's not exactly to 0. And that's why you are able to do it. And that's why its answer is 0. Similarly, look at the question number 4. It says that so that limit n tends to infinity 2n square plus 3 divided by 3n square plus 5n equal to 2 by 3. So this is the, look at expression. This expression is nothing but it's a rational one. And what we will do, we will take the maximum power of the n, right? And divide each term by that one first. So 2n square plus 3 divided by 3n square plus 5n. In this expression, n square is the maximum, has the maximum power of n, that is 2, right? So I will divide each term by n square. So dividing each term by n square, so 2n square become 2, 3 is equal to 3 by n square, and so 3n square become 3 and 5n become 5 by n. Now take the limit and use the algebra of limits. So limit n tends to infinity 2n square plus 3, 3n square plus 5n becomes each one. So using here as a quotient of that limit, right, where bn is not equal to 0. This will becomes out to be limit an divided by limit of bn, and this will be, so I am going to use this one. So in the nominator, take the limit n tends to infinity 2 plus 3 by n square, and in denominator limit n tends to infinity 3 plus 5n. So this will become 2, this is a constant thing, 3 by n square becomes 0, and this 3 is constant, and 5 by n become a 0. So what it will comes out? It will comes out 2 by 3. So this is the correct answer for this problem. Now look at the question number 5. If a and be a bounded sequence and bn tends to 0. Now look at the things. The first sequence is given as a bounded sequence, while the second sequence is given as a converging sequence, converges to 0. Then the product of that sequence a and bn must converges to 0. That is the question. How to prove that? We will go to use the definition of boundedness of a sequence and the limit of a sequence. That's all. So since n is a bounded sequence, therefore there exists a positive a real number a, such that modulus of n is less than n for every n, right? For each term that is less than a. That is the definition of if you go through it, this is the definition of a bounded or boundedness of the sequence. And now bn is a converging sequence, converges to 0. Therefore, by definition of a limit point or converging of a sequence, for every epsilon greater than 0, there exists a natural number m such that bn minus this limit point 0 is less than epsilon by a. So modulus of bn is less than epsilon by a. Now use equation 1 and equation 2 at the same time. So here a and bn is the sequence which is I have to prove that it is converges to 0. So this will comes out a and bn, and then this product of the two numbers or modulus of the two numbers is the nothing but it's the equality of this one, right? So this will comes out to be an is always less than a. Here you have from the first one. So an modulus of an is less than a, and modulus of bn is less than epsilon by a. You have taken from here. So this will comes out a is cancel out, and it will comes out a and bn minus 0 is less than epsilon, and that is the definition of a convergence of a sequence or limits of a sequence. So a and bn has the limit point as 0. Now question number 6. It is given that a sequence is converging and converges to a real number a. Then modulus of n, that is, if I take each term as a modulus, then that sequence also converges to modulus of a, modulus of the. This is also a good question. Why? Because this converse may not be true. We will see in a minute that how the converse may not be a true, is not always true. So firstly, let us let us solve this question. So limit n equal to a is given. So sequence n is converges to a. Therefore, by definition of a limit point, for every epsilon is greater than 0, a natural number m exists such that n minus a modulus is less than epsilon for each n is greater than or equal to m. That is the definition. So I will take these whole things and I will calculate this one. So I have, this is my sequence and this is, I have to prove that this is the limit point of that sequence. So I will take in a modulus of both these two, and which is obviously less than or equal to n minus a. How? Use this property. Here it's written one. If modulus of modulus x minus modulus of y modulus, that is less than or equal to modulus x minus y. It is always true. You can take one example. So let's say x equal to 5 and y equal to 2, right? So modulus of x is equal to 5, modulus of y equal to 2. So modulus of x minus y equal to 5 minus 2. So this is equal to 3. And if you are taking modulus of 5 minus modulus of 2 is also going to be. But since both I have taken as a positive number, that's why it is not coming in a special role. But look at this number. Take x1 as equal to minus 5 and x2 equal to minus 9. You can say this. Or let's say 2, right? So modulus of x1 become minus 5. Modulus of x2 become 2, and henceforth modulus of x1 minus of x2 modulus of x1 minus of modulus of x2 modulus is equal to modulus of 5, modulus of x2 is equal to 5. So this is 5 minus 2 equal to 3. But what will be the value of modulus of x1 minus x2 modulus? So x1 equal to minus 5, x2 equal to 2. So this is minus 2 modulus. So this will comes out to be modulus minus 7. This is equal to 7, which is always greater than and equal to always greater than 3. So that's why this theorem is always valid, and this is a very special inequality you have to remember for further questions. So that will gives us that modulus of n minus modulus of a is less than epsilon, and henceforth this sequence modulus n converges to modulus a. That's the proof of this theorem. Converse may not be true. So minus 1 by power n, take the minus 1 by power n as a sequence. This sequence has a terms as minus 1, 1, minus 1, 1, 1, but it is a bounded sequence. Take modulus of each an. Modulus of each an becomes 1, 1, 1, 1, 1. Modulus of an converges to 1, isn't it? It's a constant sequence, that's why it's a converging sequence. But n is not a convergence sequence. N is not a convergence sequence. So prove that n tends to 0 if and only if modulus of n tends to 0. This is also a good question. And how to prove that? Use the definition of limit of a sequence to prove this one. For every epsilon is greater than 0, there exists a natural number m such that n minus 0, that is modulus of n, is less than epsilon. And in the previous questions we have already shown that it is nothing but it is, I can write this one as a modulus of n minus of 0 modulus. So modulus of n tends to 0 leads to modulus of n tends to 0. Vice versa you can also true. So start with from here, you will get this equation, you will get this one, and that means modulus of n implies n tends to 0. So once you have a modulus of n implies 0, this also implies n implies 0. Just reverse it. Now question number 8, I am just going to read it. So if n is a converging sequence and bn is a diverging sequence, then so that limit an by bn equal to 0 and an plus bn is divergent. Sum of this converging and diverging sequence is always divergent, but the quotient by converging by diverging sequence leads to 0. And we will show in a minute that how I can be sure about this solutions. So, since an is given converges, therefore it converges to L. So, suppose its converging point is L and Bn is diverging. Let us for a time being, let us suppose that it is diverges to plus infinity. Then limit an by bn, use the algebra of limit for quotients. This will gives you L divided by plus infinity and this will leads to 0. That's the first one. But look at in the second one and you use the algebra of limits for addition. So this will addition to L plus infinity and this is infinity. That means an plus bn is diverging sequence. Now look at the problem number 9. This is one of the good problem and it's always asked in a exam, and it is good to use all the time. What is given? If r is greater than 1, then prove that limit n tends to infinity r by power n is a diverging sequence, that is plus infinity, diverges to plus infinity. And what will be the value of r? Remember this one, r is strictly greater than 1. So if I put r equal to 1, what happened? 1 by power n. What happened? It's become a constant sequence and it is equal to 1. Anyway, so since r is greater than 1, take r equal to 1 plus s. I can write this one, right? For some h is greater than 0. So Rn can be, why? Because r is greater than 1, therefore h must be greater than 0. And Rn can be written as 1 plus h by power n. And now expand this 1 plus h by power n. 1 plus of nh plus half of n into n minus 1 h square and so on plus of hn. So this will truncating all those terms and taking these two terms. So Rn is also greater than this term, right? Because Rn has plus of this. These are the plus in this one. Therefore, Rn must be greater than 1 plus of nh. And why I have taken two terms only? You can take 2, 3, 4, 5, 6. It's up to you, but in general, to simplify the equations, you have to take the two terms. That's enough. So let if g is greater than 0 be any number, however large you can think about it, then 1 plus nh is greater than g. And if n is greater than 1 beta h, g minus 1. If n has the value 1 beta h g minus 1, then 1 plus nh is always greater than capital G. Let m be a positive integer such that it is greater than of 1 beta h g minus 1. So I can choose this natural number m such that this is greater than 1 beta h into g minus 1. This will gives me 1 plus nh is greater than capital G. And if it is happen, then that means this is Rn is also greater than capital G. If each term of a sequence is greater than however a large number, then that sequence must converges to plus infinity. That is our study previously. Now look at question number 10. So find limit 2 pi power n and limit 3 pi power n. Use the r is greater than 1. So both are going to be infinity. Now look at this question, 11th question. If two sequences an and bn such that an plus bn and an into bn converges, then so that an and bn may not converge. That's a very good question, isn't it? So if you have a two sequence and addition and product are converging sequence, so converges to some points, some different points or some same points, it doesn't matter. But you must show that it is not the case that an bn always converges. It may not converges. So look at one example. I have taken this one, an as a minus 1 by power n, and it is not a converging sequence, even though it is a bounded sequence. And bn equal to minus 1 by power n plus 1, it is also not a converging sequence. And n plus bn, what it happens? It will gives you a constant sequence 0, 0, 0. So it's going to be a constant sequence, it's a converging sequence. An bn, this is going to be minus 1. So let me explore this one. So what we are talking about? We are talking about minus 1, 1, minus 1, 1, minus 1 and so on. This is our first an. and the second one minus 1 by power n plus 1. So this become 1 minus 1, 1 minus 1 and so on, right? Now term-wise addition will give you 0, term-wise addition will give you 0, 0 and 0. So it's a constant sequence, and term-wise product is going to be minus 1, minus 1, minus 1. So that is the very easy to do this. Now this will be the last one. So question number 12, and it is always recommended to solve these questions. And why? Because we are going to use one inequality which is not very frequently used, and that inequality is maxima and minima of two numbers a and b. So if it is given that a question has been asked that there are two sequences a n and b n such that they have converged to at two different points a and b, then if I choose Sn and Tn as maximum of an, bn and minimum of an, bn, then so that Sn and Tn are also convergent, and moreover it is converges to the maximum of AB, the limit points, and minimum of AB, that is minimum of AB. So if I prove one on the similar line, you can prove the second one. So I will prove for the Sn. So use this. If we have a two real numbers a and b, then maximum of AB is nothing but it is half of a plus b plus of half of modulus of a minus b. That is always true. And minimum of AB is nothing but half of a plus b minus of half of modulus of a minus b. And that is also true, right? So Sn, what is the Sn? Sn is the maximum of two sequences a and bn. So I can write this one, maximum of a and bn, maximum of a and bn. What does it mean? That means half of a and bn plus half of a n minus bn modulus. Now take the limit both sides. So limit n tends to infinity Sn is equal to each term, because algebra of limits gives you the give you the preference that you can use the limit each term wise. So limit n tends to infinity a and bn plus half of limit n tends to infinity n minus bn. And what it will gives you? This will gives you half of a plus b, half of a minus b, and this will gives you half of n minus bn is nothing but half of a minus b, right? This one is here, this one is here. So maximum of AB. So that's the proof, and on the similar line you can prove the proof for Tn, which is the minimum of a and bn, and that is the one more questions. So if an is greater than or equal to 0 for every natural number n and limit an equal to L, then L must be a non-negative numbers. So for that, let possible L is less than 0 or epsilon equal to minus L is greater than 0. Since limit n tends to infinity a n L is given, therefore for epsilon is greater than 0, there exists a natural number m such that a n minus L modulus is less than minus L, and this happens for every n is greater than or equal to m. And now that means you can expand this inequality. So a n minus minus L is less than a n minus L is less than minus L, right? So a n is less than minus L plus L equal to 0. So a n is less than 0, and which is a contradiction since you have already chosen that a n is a non-negative terms. So that means this contradiction leads to that L must be greater than or equal to 0, L never be less than 0. That is the theorem. The second theorem, a n and b n be two sequences such that a n is less than or equal to b n, then limit a n is less than or equal to limit b n. Use the same type of techniques where you have a n, b n, then that means I can write this b n is greater than a n, b n minus a n is greater than or equal to 0. Taking both sides limit, this will gives you limit b n is greater than or equal to limit a n, and that's how the proof is, right? Similarly, a n, b n and c n be three sequences such that a n, b n and c n. It's also called sandwich theorem. Sandwich one, right? So as you can see here, if a n is L and c n is also L, then b n must converges to the same number L. Proof is quite easy. So for every epsilon is greater than 0, a n is converges to L and c n is converges to L is given. Therefore, there exist two numbers, two natural numbers m1 and m2, for which taking the maximum of m1 and m2 This will leads to you L minus epsilon is less than An is less than L plus epsilon, and similarly L minus epsilon is less than Cn is less than L plus epsilon. Merge both two equations and it will comes out L minus epsilon is less than An is less than and equal to Bn is less than and equal to Cn and is less than equal to L plus epsilon. So as you can see here, for epsilon neighborhood of L, all these sequences lies. All these sequences lie. These are given. So this is Bn is here. So Bn minus L is less than epsilon. That means the sequence Bn must converges to the same number L. So thank you so much for listening.